Hey, how you doing? My name's Elton. Welcome to Learn Docker in a Month of Lunches. This is episode 5, and we're going to be talking today about the container file system, specifically working with stateful applications and how Docker stores state. So this is a particularly important topic, especially if you're new to Docker, because the container file system works differently from other file systems that you've worked with for virtual machines and other types of runtime. And especially people who are new to Docker can get kind of confused about where these files come from, what happens when you write files into a container, and how you can have the files that you care about living outside a container, so that when you upgrade your application and replace your V1 container with a V2 container, the data still carries on. So that's a kind of important thing if your application writes some state. Okay, so let's go and look at the slides for today. So usual format. If it's the first time you've seen the episode in the series, I'm going to walk through quickly the homepage for the book. So this whole series is based on my new book. So I'll read a chapter each episode. DIAMOL.net is the website. We'll have a look at what's on there. There's a bunch of links. There's a couple of interesting things that I'll point out today. Mostly I'll be going through chapter 6 of the book, which is using Docker volumes for persistent storage. So actually there's two main themes here. There's Docker volumes, which are this unit of storage that you can attach to a container. But in order to understand volumes, you really need to understand how the container file system is built. So we're going to be covering both those things. So as usual, there's a Q&A that I'll save to the end. So if you've got any questions, put them in the YouTube chat or the Slack channel, and I'll pick them up if there's a discussion to be had at the end. More than happy to help you out if you've got any questions there. Okay, and that's it. So let's get stuck in. So here's the homepage for the site, diamol.net. This is where you'll find all the links. You can buy the book if you'd like to buy the book. That would be great. If you haven't got it yet and you're watching live, then today the digital copy on Manning is half price. So instead of $40, it's $20, and you can download the PDF and all that sort of stuff if you want to do that. So if you haven't got it yet, today's a good time to get it from Manning. Look at that, eight 5-star reviews, and it's only been out for a month, so that's pretty cool. If you prefer, you can buy it on Amazon. If you do buy it on Amazon, it would be great if you left a review, because it's only just come out and there aren't any reviews yet. And people don't buy books unless there's a lot of good reviews. So if you like it, leave a good review. If you didn't like it, don't worry about leaving a review. Okay, so the other things are, there's the link here to the Slack channel where I hang out. You can ask questions about Docker or about the book. The short link to the stream, this will always take you to the latest one. There's a giveaway, so I've got some copies of the book to give away every week. If you're done with Docker and you want to know what's next, then my next book is called Learn Kubernetes in a Month of Lunches. And right at the end here, if you're there's a link to all the episodes that I've done so far of the series, and a YouTube playlist with them all involved. And if you're wondering what my credentials are to talk about this stuff, there's a little bio there which I've just added today. So I'm a Docker captain, so that's like a recognition program that Docker have. I used to work with Docker I worked at Docker for 3 years, and I've been using containers since 2014. So like I'm a freelance consultant and a trainer. I use containers, Docker and Kubernetes like day in, day out, and I've been doing that for the last 5 years, year 6 now. The other stuff I've got, if you have a Pluralsight subscription, which is like an online training platform, then I've got a ton of courses on there covering stuff like in and around the container ecosystem. So my most recent courses have been to do with Prometheus. There's a bunch of stuff about Jenkins there, which is a build system, works really nicely if you run it in Docker. There's an SRE course in there, which if you're interested in that, that's a pretty good one. Really popular at the moment is Istio, which is a service mesh that uses Kubernetes. Helpful if you understand the container concepts to watch that course, but it'll give you it'll help you understand why these things are really popular. If you don't have a Pluralsight subscription, head to pluralsight.com and you can sign up for a free trial and you can watch a bunch of this stuff. Okay, I think I'm done. I'm done for advertisements. So let's get on and look at the book for today. So today, chapter 6, using Docker volumes for persistent storage. Now, containers are great for stateless applications. So when you run in production, you're going to run on a cluster, which is a group of servers that all have Docker installed, and you'll talk to the cluster and you'll say, run my web application. I want 10 containers running. And the cluster will take care of receiving incoming traffic to any server, distributing it among the containers. It doesn't matter. Oh, I'm in the wrong view. Let me switch to the right view. It doesn't matter which container receives the request because they all start from the same image. They've all got exactly the same application running, exactly the same configuration. They all behave in the same way. So it's great for stateless applications, but you can do storage inside containers too. So if you've got older applications that aren't stateless and they rely on writing to disk either as a local cache or for persistent storage, you can do that too in containers. but you need to understand how all this stuff works. So this is a really good example of an aspect of Docker which will trip you up if you don't understand the principles, and that's what we're going to go through in this chapter. Okay, so when you run data, when you run a container, it has its own file system. So if it's a Windows container, it has a C drive. If it's a Linux container, it has a slash root directory. And the contents of that directory are whatever's come from the image. So and although you can run multiple containers from the same image, they each have their own copy of the file system. So we'll see that as usual with these chapters. Like, it's tons of exercises, so we're going to get right into the exercises and see this stuff in action. So let me scan over here. Today, actually, I'm running Windows containers. So this chapter, there are some, because Windows and Linux have different file paths, there are some differences around that. And I want to show you all the examples. Docker Windows doesn't do anything. What I wanted to do is Docker version to show you that I'm running, the client is Windows and the server is Windows. So when I run my containers, it'll be Windows inside the container. Up until now, I've used Linux containers, just to show you that all the examples in the book are cross-platform. So I'm going to run this here. So Docker container run. There's nothing new here in this container run command. You've seen this from episode 1. You've also seen me failing to copy and paste correctly. So I'm giving it a name, rn1, and it's from this image called DIAMOL ch06 random number. I've already pulled the images for this chapter for today so that we didn't have to wait and see these things downloading, but the output will be the same for you if you run it without downloading the images first. As you've seen previously, Docker will pull the image if it doesn't have it locally. So I've run one container from this image. I'm going to run another container, exactly the same image, different container name, but the whole package of the application is the same between rn1 and rn2. All these applications do is they write a random number to their local disk inside the container, and then they exit. So if you remember the types of container that we talked about, these are like task containers. They do a single task and then they end. Okay, so if I go and see what we're doing here, if I do a Docker container list, then we will see that there are no active containers. But if I do, honestly, if I do the all flag, then you will see that they're still there. So I've cleared everything down before I started. These are my two rn1 and rn1 and rn2 containers that exited a minute ago. And they're no longer running. So if you remember way back in episode 1, I showed you that when a container has completed the task that's running inside the container, when the application process exits, then the container exits. Doesn't use any CPU or memory because it's not running anymore, but the disk still exists. And we'll see that in action now. So there's this Docker container copy command. And Docker container copy will let you copy files out of the container file system onto your local machine, or vice versa, from your local machine into a container. And the syntax is Docker container copy, and then the source. And if the source is a container, then it's the container name with a colon, followed by the path of the file inside the container. So I'm copying rn1 from the rn1 container, the file that was written when the application ran. So it's just a random number. I'm copying it to my local machine to a file called number1.txt. Okay, I'm going to copy the one from the second container called rn2. So each of these wrote a container in the same place in their own file system, and I've copied them to my local machine now. And if I cat those files to see the contents, I've got number 1 is 391 and number 2 is 457. So all this app does is writes a random number to a file. But the purpose of showing you this is it makes it really clear that even though the image is exactly the same, the command is exactly the same. When these containers start, they do the same thing, but each one generates a different random number and writes it to its own container file system. The file system continues to exist when the container's stopped, so you can access that, and I can copy those files out, and I can see that they are different. So same image, independent file systems for every container from that image. Okay, so you've seen how we look at this when every exercise in the chapter has a screenshot showing you what it looks like. So if you do have problems running one of the exercises, and hopefully you don't, then you can have a look at what I did, and you'll see the difference hopefully. Okay, so here's an important diagram that I'm going to focus on just for a second here. So the reason that each container has an independent file system, even though they're from the same image, is because the container file system is built up from different sources. So we know that when you start an application in a container, Docker creates the environment for that application to live in. That is the container. We know that it creates like a virtual IP address. It connects it to a virtual Docker network. And it also builds a virtual file system for it. The file system starts from the container image, so the contents of the image. So in this case, my random number app has only got two layers in there: the base operating system and the application layer itself. That's a simplification. There are probably lots of layers, but those are the main things. And then each container starts off with a copy of that file system, which is the image, the data from the image, and it has its own writable layer. So every time you write data inside a container, it lives in its own writable layer, which is why random number container 1 and random number container 2 could write to the same file in their own file systems and have different contents. They're actually separate file systems in those writable layers. So they share the image layers from the image. They share those layers from the image, but on top of that, they each have their own independent writable layer. Okay, right, important point. So we'll come back to that in some more diagrams later on. Okay, so when we stop the container, the file system still exists. When I remove the container, it gets deleted. So that's something to bear in mind. So when we see that if you remove a container explicitly, then the file system goes as well, and that writable layer is gone. So any data that was written inside the container no longer exists. Now we know also from the episode about building images that image layers are shared, and they're shared around by they're shared around between containers and between images. And for them to be shared, they have to be read-only. So image layers are read-only for the caching to work. So when you edit a file inside a container, it doesn't edit the image. So if I start a container from an image, change some files, and start another container from the same image, it will start off with the original image contents, not the changed contents. So when Docker, when you edit a file from one of the image layers, Docker has this copy on write process, which means it copies the file from the image layer up into the writable layer, and then it overwrites it inside the writable layer. And then it kind of hides the file that was inside the image layer. So another container starting from the same image, it just has the original image contents. It doesn't have the overwritten file. It's a nice, neat way of getting around the fact that image layers are cached and shared and read-only, but obviously every container needs to be able to edit its own file system. So again, we got some exercises to show that in action. Nice. These are all nice, simple exercises, just writing files around so we can be clear about what's living where and how you interact with it. Okay, so I'm going to run a completely different container here. All this does is it reads the contents of a file inside the container file system, and prints it out. So it's just a URL. So there's a text file inside the container image called url.txt. And when the container application runs, the command for all the Docker files are in the source code. You can go and explore and see how these are actually done, but they're not really the focus, so I'm not going to focus on them in the chapter or in the episode. So that's all it does. It just prints out the contents of that file and then ends. Now, if I do create an alternative for that file, so if I if I echo out a different URL to a file called url.txt, and I do a Docker container copy. So what I'm doing here is when I ran that container that printed out the URL, I gave it the name F1. What I'm doing is I'm copying the other way around. So the source now is my local file called url.txt, and the target is the F1 container. And the root, in the root of that container, which happens to be C:/ because it's a Windows container, but Docker takes care of the paths for me, it's going to overwrite the contents of that existing file. So around the container, it exited, its file system still exists. There's a file there at the moment inside that container file system called input.txt, which has the URL for the book. And I'm about to overwrite that file with the URL for my own name, which I think doesn't actually resolve to anything at the moment. So I need to sort that out. So I've copied that file in. I've overwritten the file inside the container file system. Now, if I start the container again, so the Docker container start command will effectively restart an existing container. So my F1 container, it's still there. It's not running at the moment. It's in the exited state. If I run Docker container start, all Docker will do is execute the command instruction that's in the Docker file, that's in the image, to start it up again. So it's going to run the same command, which is to print out the contents of that URL text file. But this time, it prints out the updated file. So I've updated the file inside the container, and I've copied in the alternative version from my local machine. When the container starts, it sees the new version that's in its file system, and this is the copy on write thing. So inside that file system, there's the image layer, which has the url.txt file, the original file, and that's been hidden inside the writable layer with a new url.txt file. So when the application reads it, it sees the overwritten file, which hides the existing file, the previous file from the container image. Okay, so that doesn't change the image itself or anything like that. So all this is doing is affecting that one container's file system. Okay, so now we'll see that clearly if I run another container from that same image. So same file display image, this is container F2. What this is going to do is it's going to show me the original URL, so the URL for the book. So when I edited the contents of that file inside the container F1, that didn't change the image, obviously, because the image layers are read-only. And when I run a new container from the image, I'm seeing the original data. Now, if I remove my F1 container, if I can actually grab the exercise, that's going to delete the file system. So rm-f means remove the container. The -f flag means even if its application is running, get rid of it. Removing the container deletes its file system. So if you've got containers that have exited, their file system still exists, so it's still using disk space. And if you don't clean up your Docker system, you can find that it ends up using a lot of disk space, because Docker doesn't explicitly remove anything unless you tell it to. So for all Docker knows, when that container exited, it might have some very important data in the file system. So it doesn't delete the file system when the container exits. It leaves it there for you to tidy up when you're sure you don't need it anymore. So now I've deleted my F1 container. If I try and access the file system, obviously it won't work because there is no container anymore. So that updated url.txt file with my name in the URL, that's gone. It's gone forever, which is okay in this case. Probably not okay if that was a SQL database in a container and I had some test data that I wanted to use for another release. Okay, so changing a file in a container doesn't update the image. It creates a copy in the writable layer and it only affects that one container. When you delete a container, when you remove a container, the file system's gone. Any changes that were unique to that container, they're gone and they're irretrievable. Something to bear in mind as you start working with these things. So this is the important point here. This is the important thing to remember. The container file system has the same lifecycle as the container. So anything that you've edited or created inside your container while the app was running, if it's just part of the container file system, it's gone when the container's gone. And there are other mechanisms to work with storage if you need your data to live independently of the container. We'll cover that later on in the episode. Okay, so you might not think that's a problem because you think, well, I do my container and then, I get rid of it and I'll start a new container and I'll do something else. How often do I do that? And the answer is you will do that a lot because the production workflow is when I've got a new version of my application to release, I kill the old container and I start a new one. And in a production environment in your cluster with your 10 web containers running, all the clusters, so like Docker Swarm and Kubernetes, they do like a rolling update feature. So you can say update from version 1 to version 2, and it will take down a few containers at a time and start up replacements. So you won't get any loss of service. But if there was data written in the version 1 containers, it's not there in the v2 containers. So you need to kind of bear all that stuff in mind. So that's the kind of scenario where you need to be starting at looking at separating out the life cycle of your storage from the life cycle of your runtime, your application inside the container. Okay, and that's what we're going to do here. So there are two ways of doing that in Docker, two simple ways. And I'm not talking about a cluster here. I'm only using that as an example. I'm just running Docker on a single machine. The way you can do that is with volumes and with mounts. So let's hide my console for a second and focus on the text for a second. So a Docker volume is an explicit object in Docker. So I can work with Docker images, with Docker image commands. I can work with Docker containers, and I can also work with Docker volumes. A volume, so this is, I was so proud of this line that I think I tweeted it when I wrote it. A Docker volume is just a unit of storage. You can think of it like a USB stick for containers. So I can create this thing called a volume. I can attach it to a container. That container can write a bunch of data. When I remove the container, it still exists on my volume. When I start a new container, I can plug in that same volume and it will see all the data. So it's a nice way of separating out the lifecycle of your data from the lifecycle of your runtime. Okay, when you create a volume, Docker, when you attach it to a container, Docker encloses it inside the file system. So when you run a container with a volume, part of the file system is now being stored in this volume. So I've got three sources for my file system. There's the image layers, the volume, wherever that's being stored, and then the writable layer. It still all looks like a single disk inside the application. It still all works in the same way, but physically they're stored in different places. So there are two ways to use a volume. The first is you can include a volume in your Docker file. So inside a Docker file, I can have the volume instruction and say there's a volume here called /data, which will be c:\data if it was a Windows container. What that does is it says effectively the image has the requirement to create a volume by default. So whenever a user runs a container, they don't need to explicitly create a volume or attach a volume to the container. The container will always start with a volume because the image requests it. So this is a good way of if you're writing data inside your container, a good way of making sure that the data lives if the container gets deleted. So it's a nice thing to do if you know you're writing data. You've got a stateful application that you know needs to store data. Okay, so back to the demos. Let's have a look at this one. So this is the this is the to-do list application. I hate to-do list demos because you often see people doing it with a new to show you how their shiny new application workflow to create a to-do list. And no one needs a to-do list app, but it's very easy to use as a demo. So I've got the to-do list application in this chapter. I use it all through the rest of the book and in the Kubernetes book too. So if you don't like it, you're just going to have to get used to it. So I'm going to run a container. It's called to-do1. There's nothing new in this container run command that you haven't seen. It's a detached container because it's a web application. I'm publishing a port, so when I browse to 8010 on my machine, it'll go to port 80 on the container, and the image is called DIAMOL CH06 to-do list. Again, I've already pulled the images just to make the demos flow a little bit better in the episode. Okay, so as this is inside this Docker file, it had that volume command. So if I look at a Docker container inspect, and again, we've seen that command before, it spits out a huge amount of JSON about all the setup of the container. But if I include this format tag, I can basically put in a path to the data that I want it to show me. So I'm going to do a Docker container inspect, but only show me the mounts part of the container setup. And so that will just show me this part of the spec, which says there's a volume. This is the name of the volume. So everything in Docker has this kind of huge ID. So containers have these alphanumerical IDs. So do images, so do volumes. That's the name of the volume. This is where it's physically stored on my disk. So because I'm running in Windows container mode, my data for this volume is being stored inside the C drive on my machine in this unintelligible path. And inside the container, it's being surfaced as c:\data. Okay, so the other two parts here, it's a local volume. There are different types of volume, which we'll cover towards the end, and it's writable. So you can have read-only volumes. This is saying that it's writable. Okay, so I've got that data there. If I look at the volumes, so Docker volumes are a first-class object, so I can list them just like I list containers and images. And there's that very long name. Here's the type of volume, which means it's local. It's on my local disk. So if I was in a server environment with a cluster, I might have different ways of having distributed storage and having volumes that are available no matter which server the container is running on. This is local. That means it's on the server disk where the container is running. Okay, so if I go and so in my output there, I've just showing the same thing that I've shown you here. And if I go and browse to the application now, which is on localhost 8010, switch back to Firefox. And this is my to-do list application. Oh, look, I've got an extra slash in there, extra space. Sorry. Okay, so this is it. Like, unfortunately, you're going to be looking at it for a long time as you work through the book. It's got a nice feature in here because you can add data. So I can say I want to finish episode 5, and I need to plan episode 6. So I can see all the lists that are in there. It's being stored inside a database file inside the container. So it uses, if you're familiar with it, it uses SQLite, which is just a database that's stored in a single file. You can't ever mark anything as done. So if your to-do list is like mine, you could only ever add to it. You never check things off. Then this app, you might be able to use this in your daily work. Okay, I think there's another joke in this chapter as well. We'll come to that later on. Okay, so the app stores data in this data directory. Now, because I looked at my container inspection, because I'm on Windows, I can browse to this path here. I need to make this bigger. And if I have a look at the contents of that path, I will see my database. So that database file, the to-do list.db, which is the contents of all the data, it gets created when the application runs. That's what contains my 2 tasks that I put in there. I can see it physically on my machine. And if I was to go into the container and have a look at /data, I would see the same file. So having a volume basically separates it out. But this is a volume that's been created as part of the container image that required the volume. So I've got this kind of random name. So although I can use that volume, it's hard for me to find which volume is attached to the container. So it's a useful kind of backup, but there are other ways to work with volume. So let me show you this. Let me show you the app in action. Yes, so you've got that. You've got the joke there, the never-ending to-do list. If I run a second container, oh, I've missed out a section here. So volumes declared images are a separate volume for each container. If I repeat that command with a separate container name, I'll get a different to-do list application with a different volume. So because it's part of the image spec that says when you create a container, it needs a volume, every container will get its own dedicated volume from that image. There are other ways to work with volume. So if I wanted to, I can tell a container to share the volumes from another container. So in this case, I could have 2 instances of the app sharing each other's data, which is not necessarily something you do very often, but you might do it if you have if you run a database in a container and you want to run a batch job in another container to back up the data, is the kind of typical example. So in my backup job, I would share the volumes from the database container, and then I'd be able to access the data files and take a backup. Okay, so let's just show you how this works. So if I create another copy of my to-do list application, so same command effectively. I'm not mapping the port this time because I just want to look at the files. So it's the same image, so it'll have the same thing set up on Windows here. So if I do an exec and I look at the contents of the data drive, when the application first starts, the directory is empty. It's only when you first browse to it that it creates the database file. So right now it's empty on my new container, which has its own separate volume from the first container. But if I create another container, and in this one, I'm using this volumes from flag. So the volumes from flag says, when I run this container called T3, I want to copy the same volumes, I want to have access to the same volumes that to-do1 has. So to-do1 has this volume set up with that long ID called E that was mounted inside the container file system at the path /data. Because I'm asking this container to copy the volumes from that container, or rather to share the volumes from that container, it will also have the same files available at the same target path inside the container file system. So if I look at the data directory on this container, so again, it's a completely empty application. I haven't browsed to it at all. But if I look at the data directory, I'll see that same to-do list database file that was originally written by the first container. So when you're working with volumes, there are a few different flags and a few different commands that you're going to get used to when you want to be able to explore them and look at what's going on. Volumes from is something you don't use all the time, but it's important to know about it. It's also useful for kind of debugging. So if I've got a container running, I can set up a separate container, look at the volumes that it's got there, and I can work on the data or look at the data without affecting what's running in my current container. Okay, so we've looked at volumes, we've looked at volumes from. So far, these are all volumes that are defined inside the container image. You can also define volumes separately. So sharing between containers is straightforward. The reason you would want the big advantage of having volumes, you can share them between containers, which is useful in some circumstances, but mostly what you want to do is share them between versions of the same application. So when I release version 1, it writes a bunch of data, and when I upgrade to version 2, I'm going to replace the container. So I'm going to throw away the version 1 container and lose the writable file system that was part of that, the writable layer that was part of its file system, and start a version 2 container with a fresh, empty writable layer. If I want the data that version 1 wrote to be available in version 2, I can use a volume for that. So if I show you how we do this, let's clear this down. You can do that by finding that volume with the long ID, or you can explicitly create a volume. So what I showed you here is that we use the volume inside the Docker file to make sure there always is a volume attached to the container, but you can explicitly create your own volume, and then you own the lifecycle and you can work with it independently. So it's a little bit more effort involved, but it gives you ownership of the volume and you don't have to hunt it down and find out where it is. Okay, so I'm gonna use a variable here to make the commands easier, which is what I try and do in the exercises to make it easy for you to copy and paste. So the target directory for my application is c:\data. That's where it stores the application data. If I was running Linux, I would use this command instead. I'm going to create a volume called to-do list. So again, volumes are a first-class object. I can list them, I can create them, I can remove them, I can work with them in kind of standard ways. So Docker volume create to-do list is going to create me a volume called to-do list, which just like the previous volume, it maps to a piece of storage on my machine, on my server, or my desktop in this case. But I can refer to it by a friendly name now. So I can refer to it as the to-do list volume. And so if I run another copy of the to-do list app, what I'm doing this time is instead of getting it to set up a default volume for me, I'm specifying a volume. So this -v flag is the new part of this exercise. So Docker container run -d, detach it and put it in the background. -p, publish a port. I'm using 8011 this time. -v says mount of volume inside the container file system. The volume is the source, which is on the left here, which is the name of the volume that I created. So I've just created this empty volume. That's the source. And when it gets mounted inside the container, it'll be at the directory, which is the value of this variable. So it's c:\data. So I'm saying, and if I was running on Linux, I'd be saying, mount this volume into the root at /data. So at the moment, this volume is empty. Excuse me, but as soon as I start writing data there inside the application, it's going to write data into the volume. It's completely transparent to the container, to the application. All it knows is there's a folder called /data that it can read and write from. It doesn't know it's being stored separately from the writable layer, and it's being surfaced separately from the image layers. It just looks like one big file system. Okay, so let's go and browse to 8011 this time. So 8011, this is a separate copy of the same application. So let me add some separate data here. So let me see, plan next plural site course. See the way I've weaved in another advert there. So let's do that. And if I go back to my exercise, I've added some data. So by browsing to the application, it's created the database, it stores some data in there. If I delete this container, so I'm deleting my v1 application container, but let's try that again, because I've copied a whole bunch of other junk in there as well. So let's do this. Okay, so my container's gone, but my volume's still there. So if I do a docker volume ls, so there's the random one that got created from the two random ones that got created when I ran the containers, and here's the one that I explicitly created. So that's still there. So the data it's still there inside the container. If I run a new image, so this is an update to my to-do list application, to its to-do list v2. So as we saw in yesterday, in episode 4, which was all about pushing to registries and tagging and versioning, I'm using an image tag here to tag this as v2. So it's a separate version of the application, but it's the same repository name. So it's ch06 to-do list, and I'm mounting the same volume. So the volume that was written to by the version 1 container, so it wrote its data to that volume. I'm mounting that in the version 2 container. So when it starts, it will already see all the data that was created by the previous version of the application. Okay, cool. So that's my new version. If I go and browse to the update, I'm just going to refresh this. What we will see is it's been a whole UI makeover. This was the second joke. So it's just completely different UIs. You can see that it's just a very clearly a different version of the application, but the data is still there. So the data, the content that I put in previously went into the volume. The container was deleted. The container's writable file system is gone, but the volume's still there. So container number 2 comes in, it mounts that same volume, and it gets all the data that the previous version wrote. So volumes are the way that you deal with persisting state between application upgrades, because an application upgrade is basically a container replacement. Okay, so that was that exercise there. So, and we'll see that in the usual output with the annotations here that kind of go through the same stuff that I'm going through in the episodes. Okay, so there's one thing here which I'm gonna call out. So there's a difference between the volume instruction in the Docker file and the volume or the v flag when you're running a container. They're separate things. So if you're building an image and you know it's a stateful application, and you want to have you want users of that image to know that there's data there, and for their data to be safe if they delete a container, then it's good to put the volume instruction in there. So if you are, let me go down here. If you the volume will have a random ID, but the data is still there if someone deletes the container without realizing that they're going to lose their data. So as an image author, so this is the stuff in here. As an image author, you should use the volume instruction if you've got stateful apps, because then users don't have to know that the data is being stored separately. They don't have to write their own volume mount. If you're a user, then the volume flag is better because you can control the volume. You know what the volume name is, and you can deal with it in a separate way. Okay, cool. So that's the idea behind volumes. The other way of working with state inside your container is to use a file system mount, a bind mount, which means I'm going to take an existing directory on my server and surface that into the container file system. Like logically, it's the same thing inside the container. I just see a single file system, but one of the directories is actually like a window into a directory on my server. So it's kind of like it's similar to having a volume, but the source directory on your server is something that you control. It isn't managed by Docker. So rather than create a volume and managing it through the Docker commands, you're just going to create directories, manage them through your usual file system, and kind of share them with your containers. So they're kind of useful for explicitly dealing with if I've got my Docker images, my Docker containers running on one disk, and I've got a bunch of other disks in my machine. It's a nice way of being able to say, look, I want to know exactly where my data is, and I'm going to share that with my containers rather than go through the managing your files and your directories as volumes. Okay, so let's show you how that looks, because it's a different syntax, and we're going to achieve pretty much the same thing with it. So I'm going to get and I'm going to save this inside some variables. So the source of my data directory is the local directory, the subdirectory called databases within the local directory, and the target is c/data inside the container file system. Again, there's a Linux version there which says exactly the same thing. I'm creating a variable called source, which is going to use a databases subdirectory in my local folder, and the target is the /data directory inside the container. Then I'm going to make that folder inside my local file system. So that's that. And now I'm going to run a container with a slightly different command. So you use the -v flag or the -- volume flag to mount a volume into the container file system. You use the mount flag with the type of bind to mount a local directory from your server into the file system. And in this case, the source is my databases directory that I saved in that variable, and the target is the /data directory inside the container. So it's really just like a pass-through. So anytime the container writes something in /data, it'll end up in my databases folder inside my local directory. Okay, so let's run that through and we'll see how that looks. Mounting, I'm publishing to a different port this time, 8012, because all my other containers are still running. I can't share those ports, so I'm just running a different port rather than clear down every time. Okay, so I don't need to go and browse to the application because you've seen what it looks like. If I run a curl command, curl is just makes an HTTP GET request to that URL and shows me the output. That will trigger the application to create its database file. And now if I open this up and clear this down, and I look at the contents of that databases file, here's the file that's just been created. So again, it's a different approach, and they work in different ways. So sometimes you're going to want to be able to say a very common use for this is to mount the source code on your desktop inside a container. So in certain types of application, I've got my code editor up. I'm working on my local code, and anytime I make a change, I can see that directly in my container because I've got a bind mount in there. So if it's a Node.js application or something that doesn't need to be compiled every time, then I can make changes really quickly. I can change HTML or anything like that, and I can see that reflected immediately. So it's binding my container file system, one path of my container file system, to a path on my local machine. Okay, so that's how that looks. The curl command just triggers it to run, and there's the output that I had inside the book. Bind mounts are bidirectional, so I can write files inside the container and see them on my server, which I've just done here. I can also write files in my server and see them inside the container. And you need to bear in mind here, especially for Linux, not so much so with Windows, that the file system might be permissioned. So you're going to need to understand the permissions of the files that you're writing. So let's have a look here. Your container should run in the context of a least privileged user, but depending on the image you're using, that might not be the case. There's a user instruction that you can put in your Docker file to specify a different user context where your application should run. But by default, it's usually an administrative account. So on most Linux-based images, the user that you're going to run as is root, and on most of the Windows images, the user is called container administrator, which has admin access. So being able to read and write and create files has potentially got some security considerations there. So that's something you need to bear in mind. But you can, if you only want to read files, you can bind mount the local host directory as read only inside the container. So I can just, if I just want to be able to browse something that's on my local machine and not edit it, then I can bind it as a read only container instead. So it's the same command, but there's an extra flag in there. So let's show you how that looks. Let's clear this down. And again, it's a similar exercise. So inside here, where am I? I'm in the right place already. Can't read that because it's gone off the edge. Try again. Now I'm in bind mount, so I need to go to CD inside so each the source code for the app for the book is broken down into chapters. I'm already in the chapter 6. I need to go back to the to-do list app. Okay. So what I'm going to do here is I'm going to take the usual arrangement of variables. So what I'm doing in this case is I'm going to surface a folder inside the application and to provide it with a configuration file. So I talked about when we were looking at images in like episode 2, how it's really important that your image is the static thing that contains your application. And when you run your app in different environments, you always use the same image. So inside your image, you might have a default set of configuration, but when you run your container in a different environment, you're going to want to apply different configuration settings because those things change between environments. You want the same image with all the same binaries because that's what's passed all your tests, but you can present the configuration from the environment with a mechanism like this by using a bind mount. So what I'm doing in this case is I've got inside my chapter 6 here, exercises, to-do list, config. I've got a configuration file here with an extended amount of logging. This is a .NET application, but don't worry if you're not familiar with .NET. All this is saying is the default logging level is debug, so it's going to write lots and lots of log entries. Without this, this is going to override the configuration file that the application uses by default, which uses a much lower level of logging. So when I run this version of the app, it's going to print out a lot more logs effectively. It's a simple way of showing you that you can your container can run with the environment settings from the platform where it's running, from the server that it's running on or the cluster that it's running on, and override whatever defaults are baked into the image. Okay, so I'm going to use this with a bind mount, and because it's configuration, I don't need to edit it. So let me clear this so we can see it better. So Docker container run, I'm calling it to do configured, detach, publish a port. I'm mounting a bind mount. So again, this is the source of the directory is the directory on my machine, which is that app config directory that I've just looked at, and the target is the app config directory inside the container image. So it will show that JSON file, that config JSON file will be shown inside the container file system, and this particular application will read that config file as well as the defaults, and it will merge them together. It's the same application image, but it has the ability to use default config or for you to override the config by presenting a file in that known directory. Okay, so we'll do the same thing as before. I'm just going to run a curl rather than go and browse to the site. That will trigger all the database being written, but it also triggers a whole bunch of logs. So if I look at the logs from my updated configuration in this container, I'll see there are tons of debug level logs telling me all sorts of interesting things to do with like when things get disposed by the operating system, by the application platform, so that they can then be garbage collected, all that sorts of stuff. Lots and lots and tons of log entries, which I might use in including the SQL statements that the ORM generates, all sorts of useful stuff in them, which I would maybe run like in a test environment if I was trying to track down a problem. I could run the production image, like the exact version that I'm running in production by using the same tag, but I can replace the configuration with something that I want to have locally. And in this case, I can up the amount of logging. If I look at one of the previous ones to do v2, then all that shows me are info level logs. So I don't get all that extra wealth of information, which I probably don't need to see on an ordinary basis. So, but that's the default configuration that's baked into the image. But by using a bind mount with my local config file, I can override that. And the application needs to know how to do that. But we cover that in a later chapter, a later episode. Okay, cool. So that's how bind mounts work, and the source for that bind mount could be anything that you have access to. So this is how you would deal with like shared storage across several servers if you're running Docker in multiple places. So it doesn't matter which machine the container runs on, it can access that because it might be a network file share or a shared drive on your Windows host. So it can be writing to a network drive. Again, inside the container, it's just part of the file system. So it could be that, my /data directory in the container is mounting to a drive called X on my Windows host, which mounts a network directory that's, some shared network device, some shared storage device on the network, so that when the container dies, another container can start on a completely different server and pick up the same data because it's shared, it's distributed across the network. Okay, so that's just the output from there. So there are some things that you need to be aware of with file system mounts. So a couple of things. The first thing is that you need to understand how Docker merges these things together, because there are several potential sources of the container file system. There are the image layers, there's the container's writable layer, and then in between there's layers that are surfaced from volumes or from bind mounts. Of course, you can have multiple of those. I've only shown one mount for each container that I've run, but I could have a volume mount and a bind mount and a read-only bind mount, all going to different directories. So Docker kind of merges all those together into a single file system. So what happens if you mount a directory, either from a volume or a bind mount, but that directory already exists inside the image? So inside the image, I've maybe got a directory called data, which has like an empty database file. Well, if I create a container with a volume where the target is that data directory, what happens? Well, this is one of the rare cases where it's different between Linux and Windows. So we're going to see that because it's important to get that. And I'm showing that's one of the reasons why I'm using Windows today, is so that you can see that things are not always exactly the same between the two operating systems, which is to do with the fact that the operating systems work in different ways. So as a simple example, you can run a container with a read-only file system in Linux. So if you can do that, if your application can live with a read-only file system, it's a nice security metric to have, because you just, like, no one can, if someone manages to try and attack that container, they can't write any files. So it's pretty secure. Windows has no concept of a read-only file system, so you can't do that. So there are a few things where Linux containers are different from Windows containers because Linux is different from Windows, and that's one of those situations. So we're going to show that in this nice simple demo. So I'm going to go back to my bind mount directory, cd/bind mount, and there are a few different files in here. I'm going to put some stuff into variables. So I'm going to run a container from an image which just prints out the contents of a directory. And what I'm going to do is I'm going to run this bind mount container, and just using without any extra variables. So this will show me the file system exactly as it is from the image. So inside the image, there's a directory called /init, and there are two files in there, abc.txt and def.txt, and all the command does inside the Docker file is print out the contents, the files that are inside that init directory. So when I run it without any bind mounts or any volumes, I see those two files which are there inside the image. Now, if I run with a bind mount instead, inside here, I've got a folder called new. Oh, you can't see that because it goes off the edge. Let's try that again. Now you won't be able to see it because of my head in the way. So let's try that again. So inside this folder called new, I've got different files, 1, 2, 3, and 4, 5, 6.txt. Now, if I run the same container image, so ch06 bind mount, but this time I am adding a mount, if I manage to copy and paste directly. So if you think it's frustrating watching me copy and paste, you should, remember the times you have to watch me typing. It's far worse. So Docker container run, this time I'm providing a mount. And so the source is that new directory inside my local machine. And the target is the init directory inside the container. So when this container starts, the contents of the init directory will come from my local folder instead of the image folder, which we'll see in a second. So it doesn't, you might think that they get merged and I would see all 4 files, but that isn't what happens. What happens is they get overwritten. So it's when you're mounting a directory, and this is the same for, actually this isn't different from Linux and Windows, that's the next exercise. When you mount a directory, it replaces anything that's currently inside the image, anything that's inside the directory from the image. So it hides that directory effectively. If I mounted a directory from my source, which was empty, over a directory inside the image that had files, it would still hide it. So I wouldn't see those files. And this is the same for all the container platforms. It's the same for Docker and Kubernetes. If I build up part of the container file system, if I provide a new directory, then it overrides, it hides whatever was in the directory from the image. So there isn't, you might, like the natural thing is you would expect it to be merged. So here's the slash init directory inside the image. Here's the init directory on my machine. They've got different files, so just merge them together, but it doesn't. Both Docker and Kubernetes, they hide the underlying folder from the image and they replace it with the new folder. Ignore what I said about Windows. That's the next exercise coming up. Okay, so whether you do this on Linux or Windows, you will see the same output. The directory, the contents from the image get hidden, and all you see is the contents from the local machine. Okay, cool. Now the second scenario is slightly different. This is where it is different for Linux and Windows. So what we've got here is you can also bind mount, instead of bind mounting a directory, you can bind mount just a file. And in that case, then you do get a merge, but only on Linux. So if I run this on Linux, I would see something different from what I see on Windows. I'm on Windows, so you can see how this looks. If I try and do a Docker container run, and I'm doing a mount, and the source this time is an explicit file. So the source is the 123.txt file inside my local directory, and the target is an explicit file path inside the container. If I try and do that on Windows, I'll get an error, because Windows can only bind directories. It won't let you bind a single file. If I ran this on Linux with the same syntax, but obviously with different paths. So if I was to do that in Linux, then it would work. I wouldn't get an error. So if I show you this output from Linux, which I think I did in the book. No, so I've got the Windows output. So you can see that. So when you run it, if you run it on Linux, you get a different output in this case. And it's one of the very rare situations where the Linux containers are different from Windows. It just won't let you do it because the way that Windows manages the union of all the file systems, all the sources of the file system is slightly different from Linux, and you're just going to get this error in Windows. There's zero way around that. So whether you're working on Windows or Linux or not, it's a good practice to have your binds and your volumes mounting to directories and not to do individual file mounts, just because it works differently in different platforms. So rather than use a feature which is different across Linux and Windows, if you just standardize and say when we do our mounts, we always mount to directories and we never overwrite an individual file, then it'll work the same everywhere. So rather than lots of projects start on Linux in the Docker world, and then eventually they add support to Windows later on. If you've already got the practices that mean you can work cross-platform, you won't find issues later. Okay, cool. So that's the other thing. The other thing you need to be mindful of is that the source of your volume, the source of your bind mount, might have different attributes to the file system inside the container. And this is one that's kind of rare, but when you see it, it's going to cause you problems. So, as an example, I can take a container and I can run it on a server in the cloud, and I can mount some sort of distributed object file system inside the container. So, as an example, I can use an SMB file share in Azure or S3. This is the section that I'm talking about here. I can use Azure files, and I can mount a directory inside my container that is using the Azure file system. But inside the container, it just looks like it's the ordinary file system. So it'll look like Linux or Windows file system, but they don't have all the same features. And it could be that when you try an application that you're using tries to make use of a file system feature that it expects to see because it thinks it's, an ordinary Linux file system. Actually, it's SMB. It doesn't support that feature. You're not going to see it too often, but when you do, it'll just trip you up because there isn't a nice way around it. So it's better to know that it might happen to start with. So my example here is with Postgres. Postgres is a database. And when it starts up, it writes its data and it expects to be able to use links, like symbolic links. And they're not supported in SMB. So if you run your Postgres container and you say, actually, I'm running in Azure, I want to have a distributed file system. So I'll run my container, I'll use a file system mount, and I'll mount it to my Azure Files share, which is a distributed kind of cloud storage product service. Then the container will start, and Postgres just won't run because the very first thing it does is it creates all its database files. It tries to write them into your bind mount. It tries to create these symbolic links, and the underlying file system, the Azure file system, the SMB file system, doesn't support symbolic links, so it'll just fail. And it'll take you a little while to find out why it's failed. And when you found out why it's failed, there's no way around it. You can't. This is one particular problem that you just can't fix. So you either use a different database or use a different type of file store for the source of your volume. So something to be aware of. You won't hit this until later in your Docker journey, but when you do, you'll be grateful that I told you about it because you're going to have to find it. You're going to have to approach that problem from a different way. Okay, so like I say here, we've covered a lot in this chapter, so we're already coming to the top of the hour. I've talked about how everything kind of gets built together, and Docker calls it the union file system. Actually, they used to call it that. They don't call it that so much now. But this idea that inside the container, I see this consolidated single disk, but the source of all the directories in that disk could come from different places. Layers from the image, the container writable layer, volumes, bind mounts. They can all be surfaced into that one file system. Okay, so there's a few things to just bear in mind here. So the writable layer is, every container's got a writable layer. Whether you don't have to specify it, they just all have one. They're good for short-term storage. So if your application writes data to the local disk as a performance boost, maybe, so to write a local cache file because it's faster than going to a remote service every time, then that's fine for the writable layer. So if the application would work in the same way if the disk was empty. So if the cache was empty, the application would still work, but it would be slower until it fills up the cache. That's fine. So that's a great use for the writable layer because it's not dependent on having the data. So local bind mounts are for sharing between the host and the container. So host just means the server or the desktop or the laptop where you're running Docker. Developers use it to load source code. They're really useful to see changes. If I'm working on my machine, I can see them reflected immediately in the container because it's a two-way bind mount. So it's just like a window into the file system on my machine. Distributed bind mounts, so if I'm using NFS or I'm using some other kind of shared network storage, then they're really useful, but be aware of the performance issue as well as the feature set issue. So if I'm writing to disk inside my application, it just thinks it's writing to a local disk. It doesn't know that it's a network file share. So potentially, the level of IO that you get on a network file share is going to be like orders of magnitude worse than writing to a local disk. So you can try and do it, but you need to be aware. You need to do a whole bunch of performance testing. Think about the trade-off between being able to spin up a container on any server and have access to the data with the fact that your application runs like 50 times slower. So that's something to bear in mind there. And then we've got, let's scroll down here. Then we've got this nice little picture, which I'll come back to in a second. We've got the volume mounts, which are useful to share data between containers or different versions of the same application when you want Docker to manage it for you. So I don't want to have some list somewhere that says all the storage for this application is in C/databases/whatever. I want to be able to just do a Docker volume list, and I can work out where the volumes are meant to be. That's also useful because there are different types of volume. So with a bind mount, I can mount a local, anything that's visible to my host, I can mount it inside the container. So if my host has a network file share, I can mount that inside my container. with volumes, there are different drivers. There's like the local disk driver, but there are also volume plugins to support different infrastructure. So it raises it to a more specific level rather than just having to deal with a file path source and a file path target. I can create a volume that uses, my network storage device because it has its own driver for Docker. So that, it's a more managed way of dealing with the data. And then your image layers, of course, they're the initial file system for the container. So with your and again, those layers are stacked just with the file system in the same way as when I'm using volumes and stuff. Anything that's written in a later layer will override an earlier layer. So bear that in mind. If you're writing files in your Docker file and without realizing it, you then overwrite something later on, then you won't see the original content. It'll be overwritten by the later content. And then I'm just going to skip back to that diagram. And this is like really the kind of, there could be any number of things inside your container file system. So it sees a single disk, but it's a logical disk that's built by Docker, and it could be any number of these sources all working together. So you always have the image layers because there's always an image for your container. You always have the writable layer because the container always has a writable layer. And there are any number of volume mounts and bind mounts which could have different infrastructure behind them powering the access to the disk. They all just look like directories inside the file system. Okay, cool. So I think we're just down to the lab now. So excuse me. I don't go through the labs in these episodes because like the whole point of this is that you run through that yourself. There's always a solution that you can go and read up on GitHub. This is about running a container that does a bunch of, it runs the to-do list and it already has some tasks in there. So there's a database file inside the image, and your job is to make sure that what have you got to do here? The to-do list starts off empty. You need to run it with a different set of storage options. So when you first run the container from the image, it has a bunch of tasks, and you need to run the container from the same image, so it starts off empty. And you can do that with volumes and bind mounts. So I'm not going to give you any more hints than we've already got in here. Okay, so how are we doing? We are out of questions. There's nothing much going on in the chat or on Slack. So I guess this is either just pitched exactly right, or maybe everyone's tuned out. So but I hope you didn't do that. So I hope you stayed till the end and you found it useful. Let's go back to this view. So today was all about the container file system, which seems so simple from the inside, because inside my container, I've just got my disk with a whole bunch of directories, but actually those directories can all come from different sources, and the sources that you use will depend on the problem that you're trying to solve. The whole thing about this episode is you can have stateful applications in containers, but you need to understand what you're doing in terms of managing the data, how you surface it inside the container, and what that means for your application. So the example I showed you where the application loaded configuration from a new directory, that doesn't happen by magic. Docker doesn't do that for you. Docker surfaces the file inside that directory, but your application itself needs to know to look in that directory for a set of configs. So so Docker will create that file system for you, but your app itself needs to know what to do with that file system. So that brings us to the end for today, and it's the end of the first week. So if you've been with me so far all this week, thank you very much. I hope you found it useful. I'm going to take the weekend off, so you can as well. I'll be back on Monday, and this was the end of the first section of the book. So when I planned out how I wanted this book to work, I drove it a lot from the workshops that I do. When in the old days when we used to have conferences, I used to do a lot of workshops at conferences. So I've kind of honed the learning path from that experience of what I found works with different students. This week one is really the basics. So we've learned about containers, we've learned about images, we've learned about registries, and then the thing that people that trips people up that I found most of all is understanding storage. So that's why week one ends with this slightly more complex topic, covering volumes and stuff, which we've done today. So when we come back again next week, so the next stream, if you're watching live, will be Monday, which will be episode 6. We're moving on to part 2, and part 2 is about running distributed applications in containers. So far we've run a whole bunch of individual containers. When I ran the NASA astronomy picture of the day app, I did lots of Docker container run commands. When we kick into next week, we're going to be looking at we need to look at Docker Compose, which is a way of defining multiple container applications. And when you move to using Docker Compose, you still use the same container images and the same sorts of flags that we've used so far, but it gives you a nice way of dealing with multi-container apps. So that's what we'll be doing next week. And I've just realized while I was talking, I was clicking on the book, and you can't see that, so you just have to take my word for it. So part one was about understanding Docker containers and images, and part two is distributed apps with containers. So we'll be doing that next week. Hope that was useful. Thank you for joining, and hope to see you again.